So thank you for the introduction, and thank you very much for inviting me to give this talk. So good afternoon, everybody. I'm going to present some results from the crowd project, and in particular, I will present the crowd project and the crowd architecture to begin with. And after that, I'll show you some results about intercell interference coordination and opportunistic strategies that have been proposed in crowd. The crowd project actually is about to finish. In June, we are going to close the technical activities, and then we will have the European review probably at the end of summer. So now we are ready to give results and to present results of the project. Well, let's start with the motivation of the project and the goals of the project. We have networks, wireless networks, that are becoming crowded and very crowded every day, more and more. These very dense networks are going to be heterogeneous in terms of size of the cells, in terms of users, in many kinds of parameters, including the range, the technologies, the kind of backhaul that you use behind the access network. The crowd project challenges, takes some challenges, not all of them, of course, are the possible challenges, and in particular, it refers to interference in the radio access network, the efficiency of the backhaul behind the radio access network, and the other problem, which is the high signaling for traffic management and network control. And actually, network control is one of the key issues that is tackled in the project. From the point of view of interference, what we consider, let me add that differently from most of the presentations that have been shown today, the crowd project doesn't work on the physical layer, on solutions for making better the transmission, but it works rather on higher layers, from resource allocation and higher. So our results can be combined with what has been shown today. It's not necessarily to be seen as a different thing or uncorrelated thing. They could be combined and get a higher gain together. What are the problems with the interference? It's basically, you make denser a network, you make the network denser, you don't gain in terms of capacity in a linear way, but you go towards saturations. These are some random simulations I took from some people that we have in the project. It's not really important. The thing is, this is the typical shape. You make it denser, the number of base stations in a network or the number of users, and the capacity doesn't grow linearly with the number of base stations. So what you can do, for instance, there are tools for LTE, like the ICIC, the intercell interference coordination, and in particular the almost blank subframe that has been proposed by the standard that we will focus on later. But there are also solutions for Wi-Fi, for overlapping BSS, for instance. The thing is, there is a strong need for control tools to be developed that basically leads to the definition of the crowd control architecture for the network that I will present in a minute. I also mentioned that we have to make it better, the utilization of resources in the backhaul of the network, which is related to what has been presented this morning in a couple of presentations. What is the key point of crowd in that case? That we should try to be dynamic in the provisioning of resources in the backhaul, and the provisioning of connections in between different controllers or in between different nodes in the network, including the possibility to reroute flows when it is needed because of computational problems or capacity problems. All of them can be considered. From the point of view of signaling, we have a number of issues which are related to interference, but not only. For instance, management of the network takes a lot of messages. If you just use wireless, you are going to share the wireless capacity for management and for real transmissions. In Wi-Fi and in cellular network in general, it's a bit different. So it's a technology-specific problem. If on top of that you consider mobility, even between different technologies, you have a lot of handover messages to be exchanged that have to be somehow managed by the network. So if you consider the standards as they are today, there's a lot of overhead in the signaling that goes over the air. and other things that have been mentioned today, like virtualization, migration, offloading of process. It's extra. It could be also extra messages that have to be handled in the backhaul or in the wireless access network that are not related to data transmissions, but somehow can help. So we want to go for the design of this efficient network control architecture, and we target opportunistic resource allocation schemes, multi-tier architecture which goes beyond software-defined networking. I'm a bit surprised that SDN probably didn't come up in the presentation today, but well, I understand that SDN has been proposed for switching control, for routing control, not really for something which goes lower to the physical layer. Although the way you select schemes, strategies for whatever you want, may be actually controlled through an SDN-like paradigm. So generalizing the SDN paradigm to something which is wider than the typical switch control is quite interesting because of the flexibility that it gives. And we thought we can use it, for instance, to configure the base station in LTE, the E-Node-B, or the parameters of the access points in Wi-Fi. There are actually multiple scopes of the control in crowd. We can have short-term optimization, like you change the parameters of the resource allocation schemes. Long-term optimization, in which you want to switch on and off some part of the network and decide on the distribution of resources in the backhaul, and this is what we call regional control. But also the mobility optimization, which goes with a flow time scale, in which you need to handle flows, configuration of handover or switching of different flows over different gateways because of computational issues or similar issues. So since there are these different requirements, so we basically go for a control architecture which is which has multiple tiers. Let's see. This is just a quick introduction to the architecture. From the scenarios we have identified in real life, like network that cover different areas like home, office, people moving in shopping malls, university campuses, and so on. What we identify from the observation of what happened in those scenarios is that we need quick decisions necessary, but only feasible if they are locally done. And coordination of local decision is also necessary, although it requires a structure of controllers, an architecture of controllers to be interconnected with each other. So we propose an architecture which has two tiers. One which is local and fast to make decisions which are locally and quick to be implemented, and another which is regional and slower, which is to coordinate the local decision. This is the basic thing of the crowd architecture. Some of the solutions that are being addressed in crowd are for LTE and Wi-Fi or similar technologies, but the common thing is that we have this two-tier architecture which has the so-called crowd local controller for the short-term optimization and the regional controller for medium-long-term optimization. And both controllers, both kinds of controller are basically extension of SDN controllers, like from the point of view of the paradigm that is used for the implementation of the controller itself. So the dense network, which to represent the heterogeneity, here we show with Wi-Fi and LTE nodes and routers for the backhaul part at least, is going to be composed by, in addition to the transmission nodes, controllers of two types. The regional controller that coordinates many local controllers, each of which is responsible for a region, a small district in the, this is the way we call it in the project. So we have a region divided into districts. The controller has the typical structure of SDN controller with northbound and southbound interfaces. Some of the interfaces in the southbound have to be technology specific. For instance, we need an interface for OpenFlow to the switches. We need an interface which is specific for the Wi-Fi technology or for the LTE technology. But that's exactly the scope of differentiating northbound and southbound interfaces in a controller. You can be technology specific on one side, and then you can translate what is needed to control the specific technologies into technology agnostic messages that have to go to software application running on top of the controller. Moreover, this is very modular because you can add applications without knowing what is the specificity of the technology and so on and so forth, basically. But there's not going to be a talk about SDN. I just wanted to mention that this is what we are targeting then in the implementation. There's a number of control applications that have been proposed in the project, and actually I'm going to discuss about the first here, which is the enhanced intercell interference coordination control in LTE, but also about D2D relay, opportunistic relay, or opportunistic offloading of the network, offloading from the point of view of traffic, not computation. Although there are many other applications that could be implemented, and that these are basically going to be implemented for the final demo in a few months for the crowd project. So let's go to one of the technical points, which is this EICIC, opportunistic intercell interference coordination control. The problem is we have multiple base stations quite close to each other because we are assuming the scenario in which the network is quite crowded, and each user is receiving signals from all the base stations or a large number of base stations. So most of the signals received are actually interference. We're not considering distributed MIMO or stuff like that, but that could be accounted also. But consider that even if you use techniques in which we will do smart decoding, dirty paper, things like that, that you can really get rid of most of the interference, it's not possible in any case to put together all the signals transmitted and to prepare, to coordinate the transmission of everybody in order to have the possibility to run dirty paper decoding for getting rid of all the interference. So let's consider a simple case in which we are not taking this optimization, but you still have a lot of interference in any case that you will have to take care of. So what happened? The base stations are going to be close. So you cannot say that you just have interference from the first round of base stations which are around you. You have to take into account a region of base station randomly deployed or whatever that will interfere with you every time there's a transmission and downlink. And similar thing will happen for Wi-Fi or other technologies. How do you solve the problem of having so many transmissions all together to different users which are uncoordinated? In the standard, there's this solution which is called almost blank subframe, which has been proposed in order to stop the transmission of some base stations in some TTIs. Meaning every 1 millisecond in LTE you have to provide the scheduling and decide who's going to transmit or who's going to receive packets. And the base station in this blank white spaces will not transmit anything but pilots or let's say signaling controlling information, not data. The idea is that most of the activity in the air in those TTIs for when you have white spaces is not going to be used by the base station. The standard doesn't say how to select these spaces, but it says downsample the number of transmission intervals that you can use, and this way the overall interference will be stochastically reduced. But of course you can do more. Why to do it at random when you can easily be opportunistic and enforce cell cooperation, especially these days that there are a lot of tools and mechanism in order to centralize at least partially offload part of the computation to base stations or controllers which are close to the base stations. The analytical problem has been studied in many different flavors actually in the project. I just put the math here just to create some crowded figure, but I'm not going to go over it. So we start with simple analytic problem that can be seen as a bin packing problem. You have a set of objects you have to put in different bins, and you have to minimize a function, or depending how you formulate, you can also do maximization. The idea is that a bin represents a TTI, an interval in which you can transmit, and the items you can put in there are the base stations. Which base station is going to be able to transmit? You cannot put all of them because they will interfere too much. You cannot put just one because then you are not using spatial reuse. You need something in the middle. And this problem is NP-hard. In the problem that we are studying since the beginning, basically, we try to find patterns selected to help all the cells. How we do that? We basically impose that the signal-to-noise ratio, signal, noise, and interference ratio, actually you can forget about the noise, it's basically signal-to-interference ratio, the one that you have in this kind of system, is going to be at least higher, it's always higher than a given threshold. The threshold could be given because it's application specific, but in general it could be computed. This is interesting because you can do the computation mathematically and come up with thresholds that make sense given that you know what is the traffic load of a network. That's actually part of the contribution of the project. I don't go through all the analysis, but the idea is that you can formulate the problem in a slightly different language and find out that it's possible to determine, to minimize the total transmission time rather than trying to minimize the interference. If you work this way, and you know what is basically the load of each base station and what is the time horizon in which you want to serve the load, which is a typical thing that you have in cellular network, because you have to request some volume of traffic you want to transmit, or because you register to some kind of service for which it's possible to estimate what is the load, then you may have reasonably an estimation of the deadline and the volume of traffic you're going to do in the next few seconds. If you have that information, basically the problem of optimizing or minimizing the interference becomes a problem of minimizing the time needed by the set of the base station to download all the traffic that is going to be required in the next few seconds. So this problem is also NP-hard, of course, but we found sufficient condition to solve it in terms of a threshold. Okay, it's a threshold that depends on the traffic parameters. I'm not going to comment on it. The threshold could be context-specific because you can put the information on the traffic which is specific of given application, but you may even estimate what are the traffic conditions and run the same optimization problem easily. Because basically the optimization problem is based on the average load in the network or average load offered by each user. So we have a heuristic actually to solve this problem that is quite simple. Okay, so we have a list of candidate sets of base stations could transmit in a time interval, 1 millisecond. We check if this base station transmitting together generate a signal-to-noise ratio which is above or below a threshold for the worst user in the set of users of this base station. If it is okay, we can schedule all together this base station. Otherwise, we select the base station that creates the larger interference, the one that is responsible for the largest interference to the other users, and we remove that base station from the set of potentially schedulable base stations, potential base stations that could be allowed to transmit. We repeat this process, and basically we come up with a distribution of the base stations over different subframes. Each base station can be actually scheduled more than once. There's no restriction on that. And in each subframe, in each TTI or subframe, 1 millisecond, the maximum maximum interference that is caused to any possible scheduled user will be above a threshold, so that we guarantee equality to the users. The complexity of this approach is basically linear with the number of users. But it goes with the cube of the number of base stations. So it's okay. I mean, this is typical complexity for problems of this kind. The nice thing is that it doesn't go too fast with the number of users, which is going to be the thing that explodes in the network, really. So how can you implement that in a centralized or distributed way? Of course, we want to go for distributed because it's fancier, but not only for that. Okay, let me be honest. We want to go for distributed approaches because we want to avoid to have too much of load for the base station if they have to compute the scheduling of multiple users, including the users of the neighbors, is going to be quite heavy. So imagine that we have this ABSF patterns that you want to optimize, but you let each base station announce what is the pattern it's going to use in the next n frames. So if I have a base station, I tell to everybody else around me, every some milliseconds, I'm going to use this pattern. And the next base station will do the same, but so everybody knows more or less what the other users are going to do, users in terms of base stations, and can decide locally which users to be scheduled. Not only that, but also in which subframes is better for me, given the activity of the other, to transmit my packets. But this, of course, has to be iterated. Because when I take a decision, then next base station may change its decision, and so on and so forth. So it requires iteration that can be studied with the game theory. Let me check, okay. So actually, the big problem is the distributed version of the of this control problem. Does it converge? No. It depends. It actually depends on how you implement it. But if you do it as simply as let each base station take its own decision and communicate to the other in turn, one after the other, it doesn't converge. It doesn't have to converge, let's say. It's not guaranteed that it converges. What we can do is actually something which is helped, assisted by a controller, central controller. First of all, if you go for a distributed approach, the main problem is that if I'm a base station and I know what other base stations are going to do, in order to improve the quality of my users, to be silent is never a good choice. Because if I'm silent, my users don't get anything. If I talk, they may take 0 or epsilon or a lot. It depends on the channel condition, but never negative. So the selfish choice of each base station is to transmit in every subframe. So the first thing we need is a controller that tells the base stations, sorry, you cannot exceed a maximum number of subframes. You have to leave some empty space. Otherwise, the base station will take all the possible space. So we have this controller that will tell to each base station how many subframes can be used out of the cycle that has been agreed. So imagine that you can use a cycle of 80 TTIs, and you can use up to 70. That's a typical thing. So the base station will have to optimize 70 transmission in 80 possible subframes. We'll have to leave available 10 of the subframes. And then run the game. So let the base station play one after the other. What the controller can do in addition to this is to check at the end of a round of iteration, or a few rounds of iteration, is to check whether some base stations don't have enough resources to serve all the traffic and other base stations have too much. In that case, this value m of the number of subframes that can be used can be changed by the controller. The controller is actually able to see all this information together without the need of the base station to talk to each other. So in addition to this, so we have a two-tier game actually, in which we have the controller that has to somehow instruct the players and the way they can play. In addition to this, to guarantee convergence, actually, we need to tell the base station that they cannot take all possible decisions once they have to change the previous decision, but they have to do what is called a single-step best response. They can change only one thing. They can decide to switch transmission from one subframe to another, but they cannot compute from scratch their transmission path. Otherwise, it doesn't converge as well. So it's quite interesting from this point of view. We have a heuristic for this, to do this process with game theory-based process. We showed that this is a Matroid congestion game, weighted and player-specific, blah, 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 not really important. And we can show, we can actually split the problem in two scheduling problems. One is short-term scheduling, which is the base station taking the decision, and the other is the long-term scheduling level, which is the controller deciding and adapting the number of transmission opportunities of TTIs to be allowed for each base station, for which we use added increase, multiplicative decrease approach, basically. Okay. So, without going into the details, what do we really get out of this interference coordination schemes? If you take a scenario in which you are trying to download the number of the number of bytes in the shortest possible time, basically we can reduce by a factor 2 or 3 the time that is needed in order to finish the download of the traffic. We compare in this graph with our algorithm, the decentralized algorithm, which is called BSB, with frequency reduce 1, 3, 5. We have also other results, of course, on different frequency reuse, or also fractional frequency reuse. And ECE is a particular scheme for fractional frequency reuse. So it's much faster to finish and to meet the deadline to get all the data if we use this this approach. The distributed version works, of course, not as good as the centralized one, but it's interesting that it can be quite useful in order to follow the variation of the load in the system. This is another example of performance with a distributed approach. And the nice thing is that the red, which is the distributed approach we have, is quite close to the optimal, potentially optimal decision that can be taken in the network when you have like a Deus ex machina doing the computation for you. So that's the optimal. And another thing is that the results we get are also very close to what can be done with power control that we don't use, actually. We don't use because we don't want to use it, and because we think that, especially for downlink of base station, it's going to be quite hard to implement power control on the TTI on the millisecond time scale. But if you can use power control on top of it, you can combine the effect. Then, I've been talking about adapting the scheduling of traffic, scheduling in the node B that could be done actually in the node B or in the cloud, taking decision on short term and long term. You need controllers for that. That's why it's a typical thing that you may reuse the structure of controllers that I presented at the beginning in order to give a clear architecture, a clear framework to implement it in reality. We have more opportunistic strategies that can be integrated actually in the, yes, about time. Can be integrated, I would say, in this framework. And in order to be really opportunistic for what concerns the utilization of channel, like the single channel of the user could be optimized without doing any trick in the physical layer, but just selecting the user that has the best channel. So we propose for that opportunistic solution, which are channel opportunistic solutions. One, let me go quick to that, is something like this. We have LTE base station transmitting to multiple users, and some of these users don't have good channels, so they can cluster together, and they let opportunistically one of the users in the cluster here relay the traffic for all the others. The idea is that you switch the cluster head very quickly, and every few milliseconds, so that every time you can choose out of this user the one that has the best channel to the base station. This way, the LTE resources are not wasted, and if you choose the cluster opportunistically and very close to each other, actually, you can have always good performances in the Wi-Fi transmission here. Although we are studying also the interference in the Wi-Fi, interference and congestion in the Wi-Fi, because that could be the bottleneck of this kind of network. I will not present the schemes. We have multiple schemes, analysis, and so on and so forth for this. We have also strange figures, but I think this is just because of Mac to Windows conversion. So sorry about that. The nice thing is that this kind of approach, sorry, I had to run on this, can be combined with a BSF thing. And we actually are studying, and continuing studying for a demo, the possibility to have a BSF to select the base station and have to transmit, on top of which the base station will decide for clusters of users where users help each other to relay the traffic. So it's ABSF plus clustering with device-to-device communication plus opportunistic scheduling plus SDN to control all of them. That would be a good demo the moment we get it. Well, we have some nice results that really show that you can boost a lot the performance. Basically, here is in terms of finish time to complete the delivery of data, we can go down 60% or so in a real network. Well, so just to conclude, the problem we are trying to tackle in crowd is the density of the network. The solution, and whatever is behind the network, the solution is at MAC layer or resource allocation layer, strategies that could be opportunistic in the way you access the channels and you let user interact with each other, controlled by SDN-like controllers. The control heuristics could be centralized or distributed, but challenges in those cases are that we can have complex SDN extension to be implemented, and cloud-based processing issues that don't scale with the density that should be taken into account the moment you really go for implementation. So theory and solutions we have, from a point of view of implementation, we have to be honest, and we should have other money from the European community to run another project to study them. Thank you.
Okay, thank you. Are there any? Yes, there's an urgent question.
Just a question for clarification. So when you say that SDN, so it's a strange definition of SDN in my, but I find it in several places. Because actually SDN is for connectivity.
Yes, that's why we say that it is a standard. Let's say that from SDN we take the structure of the controllers.
Yeah, because actually control functions are not necessarily the same.
Yes, but
SDN is for connectivity, and then also this southbound and northbound is.
They are more generic than SDN actually.
So theoretically, SDN should be technology agnostic, and then you
and technology.
And
we mix because we. Look, to be honest, at the beginning of the project there was no SDN. We had in mind the control architecture. Then, in order to make it somehow simpler and interesting for the trend that we have today, we thought that we can sell this as an extension of SDN concept that could be integrated with SDN. Think about all this effort about controlling access points or wireless networks with SDN and the flow level. You can do it, and you have extension of OpenFlow. We actually use OpenFlow. Okay, you can say that there's not really a SDN, or OpenFlow is a southbound protocol for the southbound interface. It's not SDN. It's a case, but it's inside the set.
Okay.
But you're right. No, it's okay.
Yes. Please.
I have a lot of questions, but let me try just one. So your presentation, at least the architectural bit of it, reminded me very much of 3GPP discussions about self-organizing networks. Okay, so and the distinctions that people draw between centralized SOL, controller, and distributed SOL, which is all mediated by the NEs, the devices, and local coordination over X2. And in that context, everyone, I think there's a sort of broad consensus that the centralized SOL is carried using TR69 as the transport with the TR196 data model used to configure the nodes and the ranges of operation of the distributed algorithms in the devices. And those algorithms are more or less free running and communicating locally over X2 from base station to base station. And I wondered if you had whether you had any remarks on the relative performance advantages, disadvantages of TR69, TR196 plus X2 compared to the SDN flow control that you had proposed.
we actually don't have an answer for that because that was not in the scope of the project, to be honest. But it's an interesting question. Could be actually object of study. The thing is, although we use LTE or Wi-Fi as examples for give something that could be easily read, understood by generic readers, we are not proposing technology-specific applications. When I present EICIC, I call it EICIC because I want to remind of the LTE need and the LTE proposal, which is called EICIC. But in general, what I presented is centralized and distributed ICIC that could be applied for many things. So I'm sorry I don't have an answer for you, but that's interesting.
Okay, I think we can take this question offline.
Okay.
Thanks again.
Thank you.